This video on resonance, like the earlier one on exact equations and integrating factors, is a reproduction from an earlier video using more primitive recording equipment. Please consult the caveat at the beginning of that video, which remains valid here. Also, note that there are approximately half a dozen small mistakes in the video presentation, which, thankfully, are all very minor and totally evident. Okay, let's get to the physical systems that exhibit resonance.
In this video, we'll see that an inhomogeneous constant coefficient second-order linear ordinary differential equation can be used to model both a forced vibrating spring mechanical system as well as a simple so-called LRC electric circuit with impressed voltage. So, consider the constant coefficient equation, AY double prime plus BY prime plus CY equals F0, that's a constant, times the cosine of omega t, where A, B, C, F0, and omega are all positive constants. We know that the general solution of the equation looks something like this. So general solution, C1y1 plus C2y2 plus R times the cosine of omega t minus delta, where y1 and y2 are a pair of linearly independent solutions to the homogeneous equation. The homogeneous equation, of course, just being AY double prime plus BY prime plus CY equals 0. So y1 and y2 are a pair of linearly independent solutions, and cy1 plus y2 gives you the general solution of the homogeneous equation, and the nature of those functions is determined by the roots of the characteristic polynomial, which of course is AR squared plus BR plus C, and the roots then are R1 and R2 equal minus B plus or minus square root of B squared minus 4AC over 2A, the usual quadratic formula. The sign of those roots, whether there's two distinct real roots, complex conjugate roots, or one repeated real root, determines the nature of the solution functions y1 and y2. And the constants R and delta, of course, depend upon the original constants A, B, C, F0, and omega. For the models that we're going to develop, we will assume that B is small. So B squared minus 4AC will be negative. And then, in that case, we know what the solution functions y1 and y2 look like. They are, in fact, damped exponentials. And so y1 of t looks something like e to the minus, in fact, b over 2a times t times the cosine of mu t. Y2 is same thing with the sign, b over 2a t times sine of mu t, where mu is the square root of 4ac minus b squared divided by 2a. So those are damped exponentials. Now, the key observation is that these functions, these decaying sinusoidals, they of course have oscillating behavior, but with amplitude rapidly decreasing to 0. The remaining term, r cosine omega t minus delta. Of course, it's just an ordinary sinusoidal. And so for these reasons, the term cy1 plus cy2y2, remember that was the solution of the homogeneous equation. This is often called the transient solution. And the term r cosine omega t minus delta is called the steady state. So this is this steady state solution, or sometimes called the forced response. So remember, the solution to the inhomogeneous equation is the sum of these two. This guy is the transient solution. This one is the steady state solution to our inhomogeneous equation. So now the object is as follows. For a fixed choice of the constants a, b, c, f0, we want to choose omega so as to maximize r. That is the amplitude of the steady state response. Now the reason we want to do this will be evident when we specialize this general situation to the two physical systems that we have in mind. And so we want to describe the two physical systems. There's going to be a mechanical system and an electrical system. And they are as follows.
All right, here's the mechanical system. It will be a vibrating spring. So we have a spring attached to a bob, which we idealize as a point mass. Here's the equilibrium position, and u of t will be the displacement from the equilibrium position. And then we'll see that there are four forces acting on this system. So the first force is, of course, gravity, mg, pulling it down. There's the restoring force of the spring, given by Hooke's law, which says that the restoring force is proportional to the displacement. So it will be a force going in this direction, and the constant of proportionality will be k, so ku. There's also a force due to air resistance, which we typically assume is proportional to the velocity, so that will be also going like this, and this will be gamma u prime. Velocity, gamma is a constant of proportionality. And finally, we will assume there's an external impressed force, which will be F0 sine omega t. So you may wonder why I wrote sine omega t here and cosine omega t earlier. That's because I meant to write sine omega t earlier. Adding up the forces, writing down Newton's first law, F equal ma, which is, of course, mu double prime, we get the differential equation mu double prime plus gamma u prime plus ku equals F0 sine omega t. So that's the second order linear constant coefficient inhomogeneous equation that models our vibrating spring. It's similar to what we wrote down on the earlier screens, with m, gamma, and k playing the role of a, b, and c. And remember that our problem is to choose omega so as to maximize the amplitude of the steady state response. But before we do that, let's look at our electrical system.
That's a simple circuit, LRC circuit. You'll see where the LRC come from. So it's usually depicted by a picture, something like this. So a typical electrical circuit. You got the current running around. This guy is the resistance for the R, the resistor. This is a capacitor, capacitance C. This is an inductor with inductance L. And here's our impressed voltage, which may depend on time. That will be F0 sine omega t. And the usual Kirchhoff's law applies, that in a closed circuit like this, the impressed voltage equals to the sum of the voltage drops as you go around the circuit, and the voltage drops occur at the resistor, the capacitor, and the inductor, and they are respectively IR, where I is the current. That's from the resistor. Q over C from the capacitor, and the voltage drop in the inductor is usually, it's always L times di dt. And so if you add them all up, you get the equation E of t equals the sum of L di dt plus Ri plus Q over C. And then we use the standard fact that the current is, in fact, the derivative of the charge with respect to time. And so if you plug that into this equation, you get your second degree equation, L times I double prime plus Q double prime plus RQ prime plus Q over C equals E of t. And so again, we have a second order inhomogeneous constant coefficient differential equation which models the electrical circuit. And so both the mechanical system and the electrical system modeled by the same sort of differential equation. Again, a constant coefficient second order linear inhomogeneous differential equation. And remember now, the object is to pick the frequency, the impressed frequency, omega, in such a way as to maximize the amplitude of the response in the steady state. To motivate how that goes, we look at an idealized situation in which there is no resistance. So let's assume that B equals 0, no resistance. Then our second order equation just becomes 8y double prime plus cy equals f0 sine omega t. So again, an homogeneous equation, but this time it's easy to solve the homogeneous equation. The solutions there are just c1 cosine omega 0 t plus c2 sine omega 0 t, where omega 0 is equal to the square root of c over a. Then the solution of the inhomogeneous equation, so inhomogeneous solution, is equal to, well, we'll write it this way, R0 cosine omega 0 t minus delta 0. That's the homogeneous term. Plus plus cosine of omega t minus delta. Okay? So notice there's no transient state here anymore because the k exponential is gone. And this, what I've written down, is true provided that omega is not equal to omega 0. But clearly then we can maximize the amplitude of the inhomogeneous part by taking omega equal to omega 0. So if omega equals omega 0, then what happens? Then a t gets introduced right here. Okay. So then in the analog of the inhomogeneous part, we now have a polynomial term, a monomial term, and clearly the amplitude is getting bigger and bigger and bigger. And this suggests that when we put the resistance back in, then omega should be, if not equal to omega 0, then at least very close to it. And so that's what we now want to test. Okay, so let's go back now to A with resistance. And remember, we're assuming that b squared is less than 4ac. B is small, and we will continue to denote by omega 0 the square root of c over a, even though b is not 0. This number then is usually called the natural frequency of the system. Okay, so then we know the general solution of an equation like that is in the form u of t plus r cosine omega t minus delta, where u of t is the general solution of the homogeneous equation, which is comprised of damped exponentials. So u is damped exponentials. Sinusoidal functions multiplied by an exponential with a negative coefficient. And recall again that goal is to choose omega so as to maximize r. Well, we use the method of undetermined coefficients. Remember, A, B, C, F0, omega are given. We can determine R by the method of undetermined coefficients because we have a constant coefficient equation, and the right-hand side is one of the types that undetermined coefficients works on, namely a sinusoidal. And it turns out that that's a rather nasty algebraic problem. It's just calculus and algebra. I won't go through it, but if you do, here's what comes out. R is equal to F0 over the square root of A squared times omega 0 squared minus omega squared all squared plus B squared omega squared. Okay, so that's the amplitude of the resulting term. And now we make a few observations. Suppose omega is, let's say, close to 0. Then what happens? This term, the term in omega goes out. All that's left is the square root of A squared omega squared. So R is approximately F0 over A omega 0 squared, which is the same as F0 over C. On the other hand, if you allow omega to get very large, so think of omega tending to infinity, then the denominator is clearly tending to infinity, and so R is tending to 0. So think of R now as a function of omega. A and omega 0 are given, F0 is given, and it's a function which starts out at this value, actually increases for a while, and then decays to 0, so it has a maximum somewhere in between. How can we find that maximum? As a function of omega, we just have to differentiate r with respect to omega, see where that's equal to 0. So if, let's write r again, r is f0 over the square root, I'll write the quantity again, a squared omega squared minus omega 0 squared plus b squared omega squared. So what's the derivative of r with respect to omega? Well, it's going to be minus 1/2 f times this mess in the bracket to the minus 3/2 times the derivative of what's inside the bracket. And if you do that, you get what? You get 2a squared omega squared minus omega 0 squared times 2 omega. Actually, I believe I switched the omega 0 is here, sorry. And so this is actually minus 2 omega. So there's a minus sign in here. Okay. But there's another term plus 2b omega. And if you stare in there, you see there's a 2 common and there's an omega common, and it will be 0 exactly when b squared is equal to 2a squared times omega 0 squared minus omega squared. Or alternatively, omega squared is equal to omega 0 squared minus b squared over 2a squared. That's the value of omega that maximizes r. Okay? Now recall, b is small. Okay? So think of it as really small, and then omega squared is just a little bit less than omega 0. Omega is equal to omega 0 minus a small number. Also, note that when b is small and omega is close to omega 0, this expression up here is very small, and this one is very small since b is small. And so I'm taking this fixed number as f0 and dividing by a tiny number, and so we get that r is rather large. And so this proves exactly what I said, namely the way to maximize the amplitude of the output of the forced response is to choose omega to satisfy this equation, which for b small is a value a little bit less than omega 0. Okay. Let me close with 2 observations. In the case of a vibrating spring system, the huge amplitude of the force response may well break the spring. Or, in the case of a bridge, if environmental conditions set up a resonance situation, the bridge might collapse, as in fact happened in the real world. The so-called famous Tacoma Bridge that collapsed back, I think it was in the 50s. However, in an electrical system, obtaining a resonant response amounts to no more than adjusting the voltage of the forced response to properly tune a radio, for example, to a specific station or frequency, that is, to obtain the strongest response to a specific transmission. And so, as we have said in the title, for electrical systems, resonance is a nice feature, but for mechanical systems, not so much.